Hello everyone, in this video we are just going to generate square pulses using PWM module of Tiva C series microcontroller TM4C123 GH6PM. Let's get started. So as the first step, let me just open the KEIL Microvision IDE for configuring a project for my microcontroller. And you can clearly see the project for the microcontroller TM4C123 has been successfully created, and I have created the main.c file required for the project. I'm just closing this, and here I just want to add the header file. Just right click on this main.c and hover over this insert has include file and then click on this header file TM4C123.h. The device header has been added. Now I'm just going to write down my main function. And inside the main function, I'm just going to create the infinite loop of the program, that is while of 1. So the programming logic which needs to be executed again and again will be written inside this while of 1, and the configuration lines will be written above this while of 1 inside the main function. And in addition to this, I'm just going to write and create or define a function called delay for producing rough delays in my program, and this is just a loop delay that we will be using in many of the programs that we wrote earlier. So we have written these types of delay functions in many of the programs that we wrote earlier in many of the lectures. I hope you remember that. Now also I'm just going to use some rough delays in my program, so only I'm just declaring and defining this function. And now here I just want to configure the PWM channel required for the PWM signal generation. So let us open the data sheet and analyze what are all the PWM channels available in this microcontroller TM4C123 GH6PM. So you can see this is the data sheet of the microcontroller that we are going to use, and in this dataset you can find a chapter called Pulse Width Modulation or PWM. And PWM module is already internally available in this microcontroller, so we can utilize this PWM module for generating square pulses of required frequency and duty cycle using this PWM module. And this PWM module is a 16-bit counter PWM module, so it will be having the value between 0 to 2 to the power 16, that is 65535, and it has totally 2 different PWM modules available. You can clearly see the TM4C123 GH6PM microcontroller contains 2 PWM modules, PWM0 and PWM1. So we are having PWM0 and PWM1 in this microcontroller, and each with 4 PWM blocks generator. So each PWM module will be having 4 PWM generating blocks, and as a total we will be having 16 PWM output pins available in this microcontroller. So let me just open one table for your better understanding. You can see these are all the PWM pinout signaling table for this microcontroller. You can clearly see this one is the motion control module 0 generator channel for PWM0, and this one is the channel 1 for PWM0, this one is a channel 2 for PWM0, this one is a channel 3 for PWM0, this one is the channel 4 for PWM0, and it goes on like this, and we are having totally 8 channels for PWM0. And this channel 0 in PWM0 is PB6, channel 1 is PB7, channel 2 is PB4, channel 3 is PB5, and it goes on like this. You can clearly see the pinouts. And if you take a closer look at the PWM1, it is also having 8 channels starting from PWM0 to PWM7. And channel 0 in PWM1 is PD0, channel 1 is PD1, channel 2 is having 2 channels. You can use either one of it, PA6, PE4, channel 3 is PA7, PE5, channel 4 is PF0, channel 5 of PWM1 is PF1, channel 6 of PWM1 is PF2, and channel 7 of PWM1 is PF3. So we very well know that to the PF1, the red LED in the tricolor LED available in Tiva C series Launchpad development board is connected, and to the pin PF2, the blue LED is connected, and to the pin PF3, the green LED is connected. So let me just choose any of the channels available in PWM1 from channel 5 to channel 7. So I'm just going to choose the blue LED, that is PF2. So I'm just going to configure the PWM1 module channel 6 for generating PWM signals of required frequency as well as duty cycle. So I'm just going to generate PWM signals from PWM1 module channel 6. So channel 6 of PWM1 module will be generating the PWM square pulses of required duty cycle and frequency. So this is what I'm just going to do. I'm just going to configure this channel for generating the required square pulses. So that's all about the data that we want to know. Now let us see what are all the steps that we want to follow for configuring this particular channel in the PWM1 for generating square pulses of required frequency as well as duty cycle. So the data pin that we are going to generate is square pulses PF2, and you can clearly see these are the 3 different types of configurations that we want to do for configuring that particular pin as PWM generating pin. First and foremost configuration that you want to do is you just want to configure the clock settings for the PWM GPIO port pin, and the second configuration that you want to do is you just want to set the PF2 pin for PWM module 1 channel 6 channel for outputting the required alternate function for PWM signal generation, and thirdly you just want to set parameters required for generating the PWM waves such as prescaler, setting and disabling the required bits for duty cycle, etc. So these are all the steps for that. And now let us configure all these things for configuring this PF2 for generating square pulses using PWM1 module through channel 6. So I'm just copying these things and I'm going to paste it right over here inside the main. So now I'm just going to perform the configuration one by one. So the first thing inside the clock setting is I just want to enable the clock for PWM module 1. So let us go into the datasheet, just deep dive into the datasheet. So as soon as you hear the term clock, just click on the chapter system control. There will be the registers that is allocated for clock of the microcontroller, and inside that go inside the register. In the register description of system control, just select the register RCGC PWM. Here is it, pulse with modulator run mode clock gating control register. So this is the register. So you can clearly see this is the register which is useful for enabling and disabling the required peripheral clock for the PWM module, and it is a 32-bit wide register, but we can only access these 2 bits. You cannot write to any other bits in this 32-bit wide register, and the first 0th bit is meant for PWM0 and the first bit is meant for PWM1. So if I want the clock of the PWM0 to be enabled, I just want to set this 0th bit to be 1, and if I want the clock for PWM1 to be enabled, I just want to set this bit number 1 in this register. So as we discussed, we are just going to use the PWM1 module. We are not going to use the PWM0. So I am just going to set the bit number 1 in this register, that is this register. So the pointer that I am going to use for the system control is as usual sysctl, and I am going to point to RCGC PWM, and I am going to write 1 to the bit number 1. So the first step is complete. Moving on to the next step, we just want to enable the system clock for port TF. So this is a usual thing that we have been doing. We have been doing this for a while in several lectures. So I just want to go to the RCGC GPIO register, and I want to set the bit number 5 for enabling the clock of GPIO port TF. So I hope you remember this. We have been doing this since the first video of LED blink. So I can also show you that register also. Here is the RCGC GPIO, and it is having 32 bits, but the only accessible bits are from 0 to 5. In this register, you can clearly see the 5th bit right over here is the bit meant for GPIO port TF run mode clock getting control. So for enabling the clock of GPIO port TF, I just want to write 1 to this bit. And the third thing that we want to do is we just want to directly feed the clock of the system clock to the PWM1 module. So you just want to choose two options. Either you are just going to use a precision internal oscillator or pre-divided clock from this main system clock, or you can use the direct system clock from the main system clock to the PWM module. So that can be done with the help of a register in the same clock control or system control tab in the datasheet. In this, you just want to go to the RCC register on the top. Here is the RCC register. You can clearly see run mode clock configuration register. In this register, you just want to select the main system clock for PWM using this bit USEPWM DIV. So let me just examine what is this 20th bit. So this is that bit. 20th bit is USEPWM DIV. So if I enable this bit, the PWM clock divider is the source for PWM clock. And if I disable or reset this bit, the system clock is the source for PWM clock. So I want this thing, that is I just want the system clock directly driving the PWM module 1. So I am just going to clear this bit. sysctl RCC. I just want to clear the bit number 20. So we have configured the PWM clock to be 16 megahertz. And we are done with the clock setting for PWM and GPIO port. Let's move on to the next configuration, that is setting the PF2 pin for PWM module 1 channel 6 for outputting the required alternate functions such as PWM. So as the first step, we just want to select the alternate function hardware for this PF2 pin. So that can be done inside the GPIO chapter in the datasheet. Inside GPIO, just click on the register description and move to the register GPIO. AFSCL. So this is the register which is useful for enabling alternate function hardware for normally configured GPIO digital pins. So you can clearly see this register is a 32-bit byte register, but we are having only active bits from 0 to 7. That is the LSB part of 8 bits is only active. You can read and write only to those bits, and each bit in this register is corresponding to a particular pin in the port as per the pointer that you are using for accessing this register. And if I'm using the pointer for port F and I'm writing 1 to this bit number 0, the PF0 pin will be associated with alternate hardware function. That is, you can clearly study this. The associated pin functions as a peripheral signal and it is controlled by alternate hardware function. So in my case, I am just going to enable the alternate function hardware, that is the PWM hardware for PF2. So I just want to write 1 to bit number 2 in this register with the help of GPIOF pointer. So the pointer for the port TF is as usual GPIOF, and I'm going to point to move on to alternate function register, and I'm going to write 1 to the TF2 second bit. And as a next step, I'm just going to make the PWM pin as output pin. And as the next step, I just want to enable the PWM output for the particular pin. So this can be done with a register called PCTL. I think here will be the register GPIO port control register. So here is the register. You can clearly see this GPPCTL register is used in conjunction with AFSL register and select the specific peripheral signal for the each GPIO pin when using the alternate function mode. So for a particular alternate function that you are enabling in AFSCL register, you just want to configure the particular function for that particular pin. So you can clearly see here I am having a pin PF2. So this particular pin may be having many functions, right? It can be acting as a digital pins, digital IOs, or it can act as a analog IO, or it can also act as any communication line, or it can also act as a PWM source, as we are going to do. So for a particular pin PF2, we are having many such functions. So for enabling any one of those functions, we are just going to use this register GPIO port control register. So you can clearly see this register is having total of 32 bits starting from 0 to 31, and it is subdivided into 8 different parts for 8 pins in a port. The bits from 0 to 3 is meant for 0th pin in the port, 4 to 7 is meant for first pin, 8 to 11 is meant for second pin, and it goes on so on, and 28 to 31st pin is meant for 7th pin in the port. And we are just going to configure the 8 to 11th bit since we are going to use the PF2, that is the second pin in the port. So what I want to write, so what is the value that I want to write for configuring this particular pin as PWM output pin? So that is provided in the page 1351. Let me just go to that page. You can clearly see here there is a table called alternate functions table for GPIO pins, and in this table you can see variety of available alternate functions for all the pins in this microcontroller. So our pin is PF2 right over here. You can clearly see here is the PF2, and it can act as a serial synchronized clock pin, PWM module 0 fault pin, PWM 1 channel 6, timer capture compare 0 channel, and TRD, which is a some communication pin. So this pin has totally 5 different alternate functions other than digital IO. So here I just want to configure this pin as PWM1 channel 6, that is M1 PWM6. So for this purpose I just want to write the value 5 to the respective field in GPIO PCTL register. So here is the table. You can see if I write the value 5, this particular PF2 will be configured as PWM1 channel 6. So let me just go to the PCTL register. So as I mentioned, I'm just going to configure this bits from 8 to 11. So I just want to write 5 right over here. So what I will do is I'm just going to write a particular 16-bit hexa value for writing 5 on this bits 8 to 11. So now what I will do is in this particular register I'm just going to write the value as a whole. So what I want is I just want to write the value 5, that is 0101 to the bit numbers from 8 to 11. So I will be writing 0101 to this bit, and 16-bit value that I am going to write to this port is 0000 0101 0000 0000. So 0500 will be my 16-bit value, and regarding the higher bits that is starting from 31 to 16 I will be assigning the value 0000. So the value that I am going to write right over here to the PCTL register is 0x00000500. So here I am just writing the hexadecimal representation, or you can just set to the bit number 10 and bit number 8, both are same, but for better understanding I am just doing this. And as the third step, I just want to enable the digital functions for the particular pin PF2. So that can be done in a register called digital enable register, that is this one. You can clearly see this is also a 32-bit register, only we are having the bits from 0 to 7 active and we cannot use any other pins. And each pin is corresponding to a particular pin in a port when you are using a particular pointer for the port. So as we know, we are just going to configure this PF2 pin as digital pin. I just want to set this bit number 2 in this register with the help of GPIOF pointer. So what I will do is I am just going to write 1 to the bit number 2 by pointing to the register with the help of GPIOF pointer. So when I write 1, the digital functions for the corresponding pin are enabled. So let me just do that. GPIOF DN, and that's it. We are done with the configuration part for GPIO and configuration part for system control, that is clock control, and now we are just going to move on to the PWM parameter configuration. So now let us start with the configuration part of this PWM1 channel 6 for generating the PWM pulse of required frequency and duty cycle. First step that I want to do is I just want to disable the PWM generation. So that can be done with the help of a register called PWM control register, that is this register. So you can clearly see from this page there are 4 main PWM control registers: PWM 0 control register, PWM 1 control, 2 control and 3 control. Why we are having 4 registers? Here is the answer. You can study this line, that is the PWM 0 block produces the MN PWM 0 and MN PWM 1 output, and PWM 1 block register produces the outputs for MN PWM 2 and MN PWM 3 channel, and PWM 2 register is meant for MN PWM 4 and 5 channel, and PWM 3 register is meant for the block for producing PWM signals in channel 6 and 7 of both the PWM channels, PWM 0 and 1, PWM blocks PWM 0 and 1. You can clearly see this N represents PWM 0 or 1, which block you are configuring, and since we are going to use the channel 6 of PWM1, that is PF2, I am just going to configure the PWM3 control register, and if you are configuring any other channel number, just configure the respective registers as per the data given right over here in this paragraph. So since I am using the channel 6 of PWM1, I am just using and configuring the PWM3 control register, and in this register you can see this is the 32-bit register, and zeroth bit is enable bit. So this enable bit right over here in the 0th bit position of this register is useful for triggering the PWM generation in the microcontroller. So if I write 1, PWM generation block is enabled, and if I clear this bit, the PWM generation block is disabled. So that's it. Now I just want to disable it before configuring the PWM channel. So since I am using the PWM1, I am just using the PWM1 pointer, and if you are using PWM0, just type in the pointer name here to be PWM0. And now I am just going to point to _T CTL register, and here I just want to clear the 0th bit, that is disable the PWM generation. And as the second step, I just want to select the down count mode of PWM counter. So since the timer is responsible for generation of PWM wave, we just want to select an option between down counting and up counting mode. So here you can see in the same register of PWM3 control register, the bit number 1 is useful for selecting the counter mode of timer for generating PWM signal. And here when I write 1 to this bit number 1, the counter counts up from 0 to load value set by us. And when I clear this bit, the counter counts down from a pre-programmed load value to 0 and then wraps up to the load value. So this is what happens. I just want to configure this PWM generation in down counting mode. So that is why I'm just going to clear this bit number 1. So I'm just going to go to the same register for clearing the bit number 1. And as a third step, I just want to set the load value for the timer for generating pulses of 10 kHz frequency. So let me just open the calculation sheet for opening and calculating the load value for generating 10 kHz pulse in the PWM channel 6 of PWM1. So now, as I mentioned, I have directly connected the system clock to the peripheral clock of PWM, that is 16 MHz. Now when I want to configure the PWM generation frequency to be 10 kHz, what I want to do is I just want to load the load value in such a way that the timer counts exactly 10 kHz time period. So time period for 10 kHz is 1 divided by 0.1 millisecond. So for each on and off time as a total, we will be having 0.1 millisecond as the time period for 10 kHz frequency. So now our task is, we just want to calculate this load value such a way that the timer will be counting exactly 0.1 millisecond as the time period for on time and off time of the wave for generating 10 kHz frequency wave. So if the frequency is 10 kHz, I will be getting time period to be 0.1 millisecond for on time and off time of the wave. And as I mentioned, I'm just going to configure the PWM timer in down count mode. So what happens is, the value will be counting from a pre-programmed value to 0. So we just want to load the pre-programmed value in such a way that it takes exactly 0.1 millisecond for the timer to reach the value 0 right over here, so that the waves that is generated in the PWM channel is exactly 10 kHz. So now what I will do is, so how I arrived this 0.1 is, if you invert this 10 kHz, 1 by 10 kHz will give me the 0.1 millisecond as the time period for the 10 kHz wave. And now the system clock is 16 megahertz, or the PWM peripheral clock is 16 megahertz, and I just want to find the time for one tick of PWM clock, which is nothing but 1 divided by 16 megahertz. 1 divided by 16 megahertz will provide me this. I'm just converting this into microseconds. You can see the value that I got is 0.0625 microseconds. 0.0625 microseconds. That's the time for one tick of the PWM counter. And if I want 10 kilohertz or 0.1 millisecond as the time period for this wave, what I want to do is I just want to divide this value by this value for arriving the load value right over here. So you can clearly see this is in microseconds and this one is in millisecond. So I just want to multiply this number by 100 before this division operation. So load value is equal to time for one tick of the timer required time period divided by time for one tick of the timer. So required timer is 0.1 millisecond or 100 microseconds divided by 0.0625 microseconds. So 100 divided by 0.025625 microseconds will provide me the value of 1600. So this is the load value that I want to load for fetching the wave of frequency 10 kilohertz. So the processing steps is simple. You just want to define the frequency of the wave that you want to generate, and you want to find the time period for that frequency. So 1 divided by 10 kilohertz will provide me 0.1 millisecond, and then we just want to find the time for one tick of the PWM clock, that is by dividing the 1 divided by PWM clock. We are arriving the value to be 0.0625 microseconds. Here we are getting 0.1 millisecond or 100 microseconds. So load value is provided by required time period divided by time for one tick of the timer. So this is the formula for arriving this load value. So now I just want to load this load value in such a way that I will be getting 10 kilohertz wave in the PWM channel 6 of the PWM1. So that is done in a register called PWM load. So this is also subdivided into 4 different registers: PWM0, 1, 2 and 3 load value registers. And as usual, we just want to configure the PWM3 since we are configuring for channel number 6. So PWM1 3 of load is equal to 1600. And here I just want to set the duty cycle in the to be 50%. So I just want the duty cycle of the wave to be 50%. So if you see clearly, the wave generated is of frequency 10 kilohertz and the time period is 0.1 millisecond or 100 microseconds, right? So if I set the time period or duty cycle of the wave to be 50%, this on time will be 50 microseconds and off time will be 50 microseconds. So that is why I am just setting the duty cycle here to be 50%. That is done in a register called compare A register, and this is also divided into 4 different registers: PWM0, 1, 2 and 3. And as usual, we are just going to configure the PWM3 since we are configuring for channel number 6 of PWM1. And here we just want to load the value of 50%, not the value 50. You must keep in mind that the load value that we are providing is 1600. So we have already provided the value of load value to be 1600. So this PWM counter will be taking exactly 100 microseconds for reaching the value 0 from that 1600 value. So this is the exact process that is happening. Every time when the PWM counter is reloaded, it will be counting from the value of 1600, and once it reaches the value 0, it will take exactly 100 microseconds for the PWM counter to reach the value 0 from this pre-programmed value 1600. So if I want the duty cycle to be 50%, I just want to load the value of 50% of this value, that is 1600. So 50% of 1600 is 800. So this will be my duty cycle value, which is 50%. So I am just loading the value to CMPA register, 3 compare register, 800. And as the next step, we are just going to set the PWM output accents required. So this is very important step. Just listen carefully what I am telling. So this is done in a register called Gen A, PWM 0 Gen A, 1 Gen A, 2 Gen A, and 3 generator A control register. So here also we are just going to configure the PWM 3 register, since I have explained this in the earlier portion of the video while configuring the PWM configuration itself. So here you can see in this register we are having totally 12 bits active, and these 4 bits is meant for a different purpose, and these 4 bits are meant for different purpose. So since I am configuring the channel A, we will be configuring only these 8 bits available in the LSP. So let me just show you the actual description of these bits. So you can clearly see this is the description for LSB 4 bits starting from 0 to 1, and this is the description for 2 to 3. Let us discuss about the bits 2 to 3, that is ACT load bits. So this field specifies the action to be taken when the counter matches the value in the PWM load register. So as I already described and explained you the process is simple. When the PWM is started, PWM block is started, the counter will be start counting from 1600 and it will reach the value 0, and once it reaches the value 0, again it will be rolled back to the maximum set value or load value, and the process continues. So this is the action, and we have calculated in such a way that if I count from the value of 1600 to 0, the exact time period generated by the PWM wave will be 100 microsecond. So that is why we have loaded the value 1600 in our load value register, that is PWM1 load value register. So this is the normal action of the PWM block, and now when I provide value of 0 to these 2 bits, what happens is when the timer count, that is PWM counter, reaches the value 0, what must be the action done in the channel? So here these 2 bits defines what must be the action taken when the PWM counter matches with the load value. So this is the load value, and when the counter matches this load value 1600, as I am using down counter, what must be my action? I want the PWM channel to be made high. So I just want to provide the value of 0x3 to these 3 bits, that is 1 1 to these 3 bits. And regarding the bits 0 and 1, these 2 bits specifies the action to be taken when the counter is 0. When the counter is 0, I don't want to do anything because the rollover happens as soon as the counter becomes 0 to the 1600. So I'm just leaving these 2 bits to be 0 0, but I'm just going to make these 2 bits 1 1, that is bit number 2 and bit number 3 of this register will be made high for making the particular GPIO pin or PWM action to be high. So when PWM counter is equal to load value, I will be making pin high. So I'm just going to go to the register of Gen A, and I'm going to set the value bits 1 and 3. And further, if you see these 4 bits, bit number 4 to 7, these 2 bits 6 to 7 specifies the action to be taken when the counter matches comparator A while counting down. So when the counter matches the comparator A right over here, I just want to drive the PWM channel to be low. So I just want to write 1 to bit number 7 and 0 to bit number 6. And I don't want to configure this thing. So I will be turning on only the 7th bit in this same register. That's it. These are all the configurations that we want to do for setting the PWM output mode. And here I just want to enable the PWM generator. So that is nothing but I just want to set the same bit that I have cleared in the first line. And as the final step, we just want to enable the PWM1 channel 6 as output of PWM generation. So here in the PWM description, channel description, register description, I just want to move to enable register right over here, and I want to enable this 6th bit so that I will be generating the PWM wave through channel 6 of PWM1. So I'm just going to PWM1 of enable R is equal to 1 left shifter by 6 times. That's all about the configurations that we want to do. Now I'm just building this project and I'm dumping the program to my Tiva C series Launchpad development board. So you can see this is the output which I got in the hardware. That is 10 kHz pulse has been generated with the on time on off time to be, and with the on time and off time to be 50 microseconds. The duty cycle is 50%. We have successfully received the waveform of 10 kHz by configuring the respective load value in the load value register of the PWM module, right? So now I'm just going to make the frequency of the wave generated to be 1 kHz. So what I will do is here I just want to change this to be 1 kHz so that the time period here will be changing to be 1 millisecond or 1000 microseconds, and the time for one tick of the timer will be the same. This is not changed, and load value will be 1000 microsecond divided by 0.6. So now when I change this, 1000 divided by 0.0625, 16,000. So 16,000 will be my load value for generating the 1 kilohertz pulse. So let me just change the value here to be 16,000, and also here I just want to change the 50% value to be 8,000. So 8,000 is the 50% value of 16,000 right over here, which will be my duty cycle. Now I'm just building this project. You can see the errors are 0 and warnings are 0. Now I'm just dumping this program to the Tiva Launchpad microcontroller. And now you can see the pulse generated is having the frequency to be 1 kHz with the on time and off time to be 500 microsecond with 50% duty cycle. And we successfully generated PWM signal of 1 kilohertz, 50% on and 50% off. And now let us try to vary the duty cycle and see how it works. So here I have generated the pulse for 50% duty cycle, right? Now I'm just going to change the duty cycle to 75%. So let's take it to be 75% means 12,000. So 12,000 is the 75% value of 16,000. So now I'm just building this project and I'm dumping it. And now you can see the duty cycle of the pulse generator is 75%. The on time of the pulse is 750 microseconds and off time of the pulse is 250 microseconds and the frequency remains 1 kilohertz. And now if I change the duty cycle value to be 25% and for 25% I just want to make the 25% value of the 16,000, that is 4,000. Now when I build this project, and I'm dumping this project, now you can see the duty cycle of the pulse generated for 1 kilohertz frequency is 25%. That is on time is 250 microseconds and off time is 750 microseconds. Thus the 25% duty cycle is achieved. So in this manner you will be able to change the duty cycle of the PWM wave generator with the help of the compare A register value right over here. So whatever the value percentage that you are giving out of this value provided in the load value, the PWM wave will be generated. If you provide 10% value of this value, 10% duty cycle will be provided, and similarly it works accordingly. And now I'm just going to write a programming logic right over here for varying the duty cycle in runtime. So here I'm just going to write a for loop which runs from I is equal to 0 to 16,000, and inside this for loop I'm just going to provide a delay, and after this for loop also I'm just going to provide a huge delay right over here. And I'm just going to declare this I variable, and inside this loop I'm just going to vary the PWM1 duty cycle. That is, I'm just going to provide the I value right over here to the PWM duty cycle register. And in a similar manner, after the delay, I'm just going to run the loop from the value 16,000 till the value 0 in the reverse manner. So what happens here is the value of the PWM duty cycle will be varying from 0 to 16,000, that is maximum value. That is, the value of the duty cycle will be varying from 0% to 100%, and when it reaches the maximum percentage it will wait here for a particular amount of delay, and after the delay the duty cycle will be decreasing from 100% to 0% using this loop, and after that it will be waiting here for another particular rough delay of time, and after this delay this process will be keep on happening because these lines are written inside the while of one of this program, that is the infinite loop of this program. So the LED which is connected to PF2 channel, that is the blue LED in the tricolor LED available in the Tiva C series Launchpad development board, will vary its brightness from minimum to maximum and again from maximum to minimum. So this will be the action of this program. Let me just build this project. So now I hope you will be able to vary the duty cycle of the PWM wave generated using the PWM1 module of this microcontroller. I hope you understood this. So there is an error. What is the error? Sorry, I just made a mistake. It is uint16. I'm just building it again. You can see 0 errors, 0 warnings. Now I'm just dumping this code to the microcontroller. The flash has been loaded successfully. Now let us visualize the output in the hardware. You can see this is the output of the logic that I have written. That is the logic for varying duty cycle. The duty cycle of the 1 kHz pulse generated in PF2 of the microcontroller, that is PWM1 channel 6 of the microcontroller, is varying from 0% to 100%. And once it reaches 100%, it is returning back to 0%. So this is the hardware setup. You can clearly see in the Tiva C series Launchpad development board, the blue LED is varying its brightness from minimum to maximum and then from maximum to minimum as per the pulse in the oscilloscope, as per the duty cycle of the PWM wave. So I hope you understood this program very well, how you can configure the PWM module of this microcontroller for generating the square pulses of required frequency and duty cycle, and how you can vary the duty cycle of the wave in the runtime of the program also. See you in the next video. Thanks for watching.